In this example, we're asked to find the diameter of a pipe for discharging water from a rooftop tank into a tanker truck. So we have this rooftop reservoir, and there's a pipe that goes down below street level and then comes into a tanker truck. We're told that the elevation difference between those free surfaces is about 2 meters. We're given the conditions of the water, what the kinematic viscosity is. We're told that it's transferring through a cast iron pipe with a given roughness. We're also told the length of the pipe, and we're told the flow rate through the system. And we're also given some information about the minor losses, like the sharp-edged entrance, and there's 6 elbows and a sharp-edged exit. We're trying to find the required pipe diameter for the given flow conditions. So this is actually a type 3 pipe system. We don't know the pipe diameter, which means we're not going to be able to calculate a Reynolds number or a relative roughness. So we're not going to be able to find the friction factor easily. We're going to probably have to iterate in this problem. So we'll analyze this with the extended Bernoulli equation, as we typically do. So let's go ahead and draw our sort of point 1 and point 2 on the picture here. So we'll choose point 1 at the top of the rooftop reservoir, and then we'll follow a stream tube as it goes out and ends up at the free surface of the tanker truck. And let's go ahead then and write the extended Bernoulli equation. So there's the total head at the outlet. That's equal to the total head at the inlet minus the head losses between those 2 points, and then we'll add in any shaft head that occurs between the 2 points. So let's go ahead and write down what we know. The pressure at 1 and the pressure at 2 are the same. They're both atmospheric pressure. Similarly, the velocity at 1 and the velocity at 2 are both approximately 0. They're very small because they're the surfaces of large tanks, so we're going to assume that the velocities there are both very small. The elevation difference, Z1 minus Z2, is equal to 2 meters. That's given in the problem statement. There is no shaft head term between points 1 and 2. There's no pump or turbine or anything like that between those points, so we don't have to worry about that. But we do have head losses, so let's write that down here. We're told some information about the head losses. First of all, we're going to have a major head loss. So there's the major loss coefficient, and that'll be multiplied by the velocity head in the pipe. V sub p bar is the average velocity in the pipe. So that's our major loss. And then we have a bunch of minor losses. We have an entrance minor loss. We're told we have 6 threaded elbows, so we'll have 6 elbows in there. Those losses all occur in the pipe, so the appropriate velocity head for where those occur is just based on the pipe velocity. We also have an exit velocity, or exit loss, sorry. So the proper velocity head there is also the pipe velocity head. So those are our major loss right here, and then our minor losses here. And let's simplify that just a little bit. Everything's multiplied by the velocity head based on the pipe velocity. So we'll just bring that outside just for convenience. Okay, so there are all of the various terms in our extended Bernoulli equation. Let's go ahead and rearrange some things just so we have it all in one equation. Actually, before I do that, let me make one other modification. Since we're told the volumetric flow rate in the problem statement, so let me go back up here. You'll see right here we're given the volumetric flow rate. So I'm going to convert the velocity into a volumetric flow rate since that's what we're given there. So where the velocity in the pipe will be the volumetric flow rate divided by the cross-sectional area of the pipe. Okay? So we can substitute all of those things back into the extended Bernoulli equation. And if we do that, making use of some of the data that we're given, we're going to ultimately get the following equation. Actually, before I do that, let me just say a few other words. You'll notice that in the head loss term, we have this friction factor. We're not going to be able to find that friction factor easily because it's going to depend on the Reynolds number, which is based on the pipe diameter. It's also the relative roughness is also a function of diameter, so that will also make finding the friction factor challenging. We don't know the diameter here. We also don't know the diameter here in, we're given the volumetric flow rate, but we can't find the average velocity in the pipe because we don't know the diameter of the pipe. So there are a lot of places where the diameter shows up, and so it makes the equation complicated to solve. So we're just going to keep that in mind as we continue to work through the problem. So let me go ahead and write down some of the known quantities that we have. We know the delta Z here, this thing right here, let's call that delta Z. So that's known. We know the length of the pipe is 20 meters, so that's given. We know these loss coefficients for the entrance, that was given as 0.5. The elbow loss coefficient is 1.5. We can look these things up in tables. Maybe they're not given in the problem statement, but we know what kind of entrance and elbows we have, so we can look those up, the values for the loss coefficients. We can find those in a table. And I guess I know the volumetric flow rate was given as 0.002 cubic meters per second. And of course, gravity is 9.81 meters per second squared. So we can go ahead and substitute these values back into the extended Bernoulli equation. So what I'm going to do is I'm just going to take this delta Z, plug it in here. Same with the head loss expression. And then I'm going to plug these numbers in. And if we do all that, we're going to get an equation that ends up looking like the following. Okay, so this is our extended Bernoulli equation once I've substituted everything in, including the numerical values. And you'll notice that we have the diameter in here, like diameter of the fifth, here's the diameter, and then the friction factor, because we don't know our diameter at this point. Okay, so I'm skipping all the steps where I've plugged the numbers into these things and I've written it all down. But again, just to kind of reiterate what it is I've done is I've just simplified the extended Bernoulli equation by plugging in everything that I know, including the numerical values. So that's how I got to this point, just a bunch of algebra. Now, some supporting equations that we'll use along the way. We'll need to be able to calculate a Reynolds number because that shows up when trying to find the friction factor. So the Reynolds number will be the velocity in the pipe times the pipe diameter divided by the kinematic viscosity of the water. So substituting in for the velocity in the pipe over here in terms of the volumetric flow rate and the diameter, and using the given kinematic viscosity that's given in the problem statement, we're going to get the following expression for the Reynolds number. Okay, so we have that expression. Let me underline these equations because we're going to refer back to them. And then the relative roughness equation relation we're going to need as well because we need that to find the friction factor. And that's just going to be 0.00026 meters because we're told that the roughness of this galvanized iron pipe was 0.26 millimeters. So this is what it is in meters. That's divided, of course, by the diameter. So we're going to need that equation as well. And we need that one because we're going to try to find the friction factor from a Moody plot. So you can see it's a complicated set of equations that I need to deal with here. And the way I'm going to try to solve this equation for the diameter is I'm going to do an iterative approach. For these kind of type 3 pipe flow problems, we typically need to rely on an iterative technique to find what the diameter is. So I'm going to just describe to you a couple of different iterative techniques you can use, but there is no one unique iterative scheme that you can use. Perhaps you can come up with your own iterative scheme that works just fine, and that's okay. I'm just going to show you two of them that I propose to solve this problem. So the first technique, let's call this iterative method 1. Is I'm going to, and my first step is just guess a value or choose a value for the pipe diameter D. And I would choose initially some reasonable value. I would not choose a diameter of 10 million miles. That would be a ridiculous first guess. Or 0.0001 meters. That would be too small. Choose a reasonable value to start with, and that'll help with the convergence of your algorithm. If you have a good first guess, that can really help. So then once I have the diameter, what I'm going to do is calculate the Reynolds number using this equation right here. Okay, that's step 2. Step 3 is I'll calculate the relative roughness. Now that I have my diameter, that's using this equation right here, so that's step 3. Step 4 is I'm going to calculate or find the friction factor from the Moody plot. Right? Because now that I have my Reynolds number and my relative roughness, I can go to my Moody plot and get the friction factor. Okay? And then I'm going to also find the friction factor using my extended Bernoulli equation. So I'm going to find the friction factor two different ways. I'm going to find it from the Moody plot using my Reynolds number and relative roughness here, and I'm also going to find my friction factor using my extended Bernoulli equation up here. Because remember, in step 1, I chose a value for the diameter, so it's pretty simple to solve this for the friction factor. So now I have two different values for my friction factor, one from the Moody plot and one from the extended Bernoulli equation. So step 6 is the friction factor from step 4 equal to the friction factor from step 5? If the answer is yes, then I'm done, which, that would be nice, right? That means everything is consistent and I'm finished. But if I'm not, if they're not the same, then I need to do another guess for my diameter. So basically, I'll just come right back up to step 1 and choose another diameter. Now the problem with this iterative scheme is it doesn't really give you much guidance on what your new value for the diameter should be. So all I know is that my friction factors aren't the same, but I don't know whether I need to choose a bigger or a smaller diameter, right, when I go back up here. So you can still implement the scheme, and I did, using a spreadsheet, and you can sort of see visually whether choosing a bigger or smaller diameter gets you closer or further from making those two things equal, those two friction factors equal. So you kind of just have to eyeball it here. It's just there's nothing in the algorithm that tells you what direction to head in for the diameter. So that's kind of a flaw of this method. On the plus side, it's pretty easy to solve the equations using this iterative technique. To find the friction factor in step 5, once you know the diameter, to solve for the friction factor is pretty straightforward. Okay, so that's the plus of this technique or this iterative method, but the downside is you really don't have much guidance on choosing a new guess for your diameter. But this is the technique I used, and let me just kind of give you some typical numbers. If you chose a diameter, your first guess of 0.04 meters, which is what I did. So a 4-centimeter pipe seems like a reasonable first guess, right? I mean, that's doesn't seem unreasonable. Then you'd get a Reynolds number, 48,800. You get a relative roughness of 0.0065 using the Moody plot. So this would be our step 4 friction factor. Using the Moody plot, you'd get a friction factor of 0.038, and then using the extended Bernoulli equation, you would get the friction factor of 0.010. So they don't match. So we have to start over again. So then I chose a diameter a little bit bigger, 0.05 meters. Okay. And then when I went through my scheme, my Reynolds number is 39,000. Relative roughness is 0.0052. My friction factor from step 4 was 0.033. And my friction factor using the extended Bernoulli equation, which is step 5, came out to be 0.068. Okay, so those two clearly don't match. In fact, they look like they're pretty far apart there. So let me do something else. Let me try a new guess for my diameter. And this one I just chose to be in between those two values. 0.045. Here the Reynolds number is 43,300. Relative roughness 0.0058. Friction factor then from the Moody plot, so that's step 4, is 0.032. And then the friction factor from the extended Bernoulli equation at step 5 also came out to be 0.032. So now they're both are equal, so now I know that the diameter I need is 0.045 meters. Okay, so that's the approach using this iterative scheme. So again, the advantage of this particular scheme that I show here is that it's easy to calculate the friction factor in the extended Bernoulli equation in step 5, because if you're guessing a value for the diameter, you can easily solve for that friction factor. The downside of this particular method is it doesn't give you much guidance on how to choose your diameters, since you're just comparing friction factors. So let me show you another iterative scheme that you can use. Okay, so this is just another way that you can iterate through this. So in this one, step 1 is choose a value for the diameter, just like we did in the previous one. Then step 2 is also to calculate the Reynolds number, just like we did before. Same thing with step 3, calculate the relative roughness. So far, the algorithm looks pretty much the same as what we did previously. And in fact, step 4 is the same as well. Find friction factor from the Moody plot. But here's where the two iterative methods are different. So far, everything's exactly the same as iterative method 1. But step 5, what I'm going to do is I'm going to solve for the diameter using the extended Bernoulli equation. And the friction factor from step 4. This is where the two schemes are different. And then on step 6 is the diameter, let me write this differently, is the diameter from step 1 equal to the diameter from step 5, coming from the extended Bernoulli equation. So if it's yes, then I'm done. If it's no, then what I'll use is use the diameter for step 5 and then go back and iterate there. So this is just another iterative method, and the advantage of this method is that it does give you some guidance on what to use for the new diameter. Okay, so step 5 here is solving for the diameter in the extended Bernoulli equation. Go all the way back up. So in this iterative method, we have the friction factor from the Moody plot. We're going to solve for the diameter and then compare that diameter to the guessed value for the diameter. If they're not equal to one another, then I'll use the diameter from step 5 as my new diameter. So this method does give you some guidance on how to choose the new diameter. The downside to this method is it's computationally harder to implement because you now have the friction factor, you have to solve for the diameter, so you're trying to solve this fifth order polynomial, which you can do, but that requires its own iterative scheme. So if you're using some sort of numerical package like MATLAB or something like that, something that has root finding methods, you could certainly implement this scheme numerically, and it's not that hard if you already have a package that can solve it for you. If you're trying to implement it in something like Excel, it would be tougher to implement because it's hard to solve this equation for the diameter d. But the advantage of this iterative method number 2 is it does give you guidance on how to find the diameter. And in fact, if I was to actually redo this with using a numerical package, like I said, MATLAB, maybe Python, something like that, this would probably be the approach I would use instead of the first approach. Either one will work, okay? And you'll get the same result. And like I said before, there may be another iterative scheme that you come up with that might be even better than what I've shown here. Okay, so you might have your own iterative scheme that might work out better than what I've done. All right, and I guess I did actually work out the numbers for this one. Let me just kind of show you the approach using this technique. So starting with the same guessed value for D. So the first iteration, I'm just guessing the first diameter there. We get the same Reynolds number that we calculated previously, 48,800. We should get the same relative roughness, 0.0065. The friction factor from the Moody diagram, this is kind of our step 4. Comes out to be 0.038. And now step 5, solving the diameter from the extended Bernoulli equation, it comes out to be 0.046 meters. So you can see that the guessed value and the diameter we get from the extended Bernoulli equation are different. So then our next iteration would be starting with the 0.046 meters, the one that we got from the extended Bernoulli equation. Reynolds number is 42,400. Relative roughness 0.0057. Friction factor from the Moody plot 0.033. And our new diameter from the extended Bernoulli equation is 0.045. So you can see I'm getting a little bit closer now to converging. This guessed value and my extended Bernoulli equation value are much closer. So let's do one more iteration. Let's see how that turns out. And if we solve for that Reynolds number, it's 43,300. Now the relative roughness is 0.0058. That friction factor is 0.032. And then the diameter from the extended Bernoulli equation, it comes out to be 0.045. So now we have our converged iterative scheme. And you'll see that that diameter, 0.045, is the same as what we solved, or what we found for using our first iterative method. So it doesn't matter what iterative method we use, we should still get the same result. It's just one iterative method may be more convenient to work with than the other one. So this is a good example for a type 3 pipe system where we don't know the diameter. And you can see we have to go through some iterations, and it's kind of complicated because we don't know the Reynolds number, we don't know the relative roughness. If you're given a flow rate, then you don't know the pipe velocity, average velocity, because you can't go between flow rate and average velocity without knowing the diameter. So it's more complex. It's probably the most complex pipe system you have to deal with in terms of type 1, type 2, and type 3 pipe systems. Okay, we'll go ahead and end the example there.